Viitorul e al tău, noi punem temelia. UTCB, construim pentru România. UTCB, Universitatea de Construcții București.
Thank you. Good afternoon, everybody. So, after these comprehensive presentations you followed until now we move to really short ones and very focused as topics. So, you heard, but I want to remind also about a big project that Japan developed here in Romania in the early 2000s. And that project was implemented by an institution, National Center for Seismic Risk Reduction. And within this institution, there was a division called Seismic Observation. And this division made some instrumentation in the country, in buildings, but also in Bucharest, with what we call seismic stations for site effect assessment. And pointer doesn't work, but you may see on the map the locations in the city where we did such instrumentation, with one sensor at ground surface and two sensors in boreholes. We had one borehole that we called shallow. Our target was 30 meters, but in practice, you cannot always meet this. There are always surprises, but roughly around 30 meters depth. And then the deep borehole, we managed to reach even 150 meters depth. But our focus today, since you are all in our university, is to show you something that is very close. In our campus, this station, where we have one sensor at minus 20 meters and another one at 70 meters. So, why we're interested in site effects? You already heard about the long period motion from 1977, inducing high amplifications for long periods, and Professor Gazetas left, but I wanted to surprise him with his image. He already showed it to you. Me, I saw it in 2006, underlining this peculiar motion from Bucharest. The reason of these motions is coming from two sources, is the deep geology and the source effects. So if we look to the geology, we know from the beginning of the century that the crystalline bedrock of Romanian plain is at about 1,500 meters in the region of Bucharest. And if we focus on the quaternary layer, we know from geologists that the thickness is about up to 200 meters in the region of Bucharest. Of course, we didn't have means to investigate at this depth, but we tried to check with array microtremor measurements that we performed together with Japanese colleagues. And you saw in the northern part of Bucharest, we tested 3 sites, and the seismic bedrock defined with shear wave velocity of 3,000 meters per second was at about 1,700 up to 2,000 meters depth. And of course, as my colleague Christian mentioned, we investigated at the surface with by performing downhole tests at all the sites where we installed borehole sensors. And in some cases, we reached over 100 meters, even 140 meters depth. What you may notice from these values is that they are not spectacular changes, and we remain in this famous class C. So the surface geology doesn't explain the amplifications in the long period range. the ground is reasonably good, let's say, from Eurocon point of view. And you can see where we are with our conference, and just a few tens of meters away, there is a small construction with a reinforced concrete floor where we have this seismic station. It was installed in 2003 with kinemetrics equipment. On the left side, you have the borehole sensors, and at the surface, we have a K2 station with a triaxial epicenter. And we started to record. The history of the station from management point of view shows that until 2010, when we closed, not us, the government closed the National Center for Seismic Risk Reduction, the management was there. Then our colleagues from National Building Research Institute took care of the station, and then from 2014 again here at the university. And at this station we recorded 33 events. 28 we can identify by date, and we have 5 records with no date because GPS didn't function well. It is not a kind of seismological station. It is, let's say, for engineers, so we have an event recording. The recording starts from a threshold that is selected. And of course, as you can expect, most of the records are coming from earthquakes from Vrancea intermediate depth. And we had the chance to record the magnitude 6 event in 2004. The smallest magnitude from Vrancea is 3.9, and we also have 3 shallow events, as you can see in the table and in the figure. On the map, you can see the yellow circles are the Vrancea events, intermediate depth, the major one, magnitude 6, and some yellow circles that are the shallow events. Of course, hypocentral distance is always around 200 kilometers because Vrancea is concentrating very well its seismic activity. And then we start to look at data. What you will see here are just preliminary results. This is an example of horizontal accelerations in the borehole at minus 78 meters. The code name is B2. B1 is at minus 28 meters, and then what you get at the surface. And overall, if we look to the big ground acceleration values, we find, of course, what was expected, significant variability of values, over 100% coefficient of variations. And you can notice average value is rather low, because even earthquake magnitudes are of around 5, most of them. The source is deep and rather far away from the city, so the level of acceleration is quite small. We were curious also to check the probabilistic models. We noticed a strong skewness, positive skewness. We checked if the log normal distribution hypothesis works. It works reasonably well, but of course you can see that our database is not so good, and there are a lot of intervals where there is a lack of data. And we were curious. This was one of the main reasons of the instrumentation, to look in more detail at the effect of the surface layers. And on these figures, you can see on the left the horizontal big ground acceleration, on the right the vertical big ground acceleration, and with the same code of colors, the values from the boreholes and from the surface. And you can notice that the clouds from the boreholes are almost in the same region. The trend lines are almost similar, so it shows that there is not a significant amplification from minus 78 meters to minus 28 meters, and that the big difference, the big increase in big ground acceleration is related to the top. In our case, top means 28 meters. But let's say close to this famous reference of 30 meters. And the figure is clear. Of course, we will check to the other boreholes and we will look to have more data. The same information comes if you start to make ratios, surface over 28 meters or surface over 78 meters, in order to check this amplification, to quantify it. And roughly, amplification is about 3 times from 0 to the bottom of a borehole. Variability of amplification is significantly reduced. But we were curious also to check if there is a correlation with earthquake magnitude, and we found practically nothing. So we cannot say that amplifications in the borehole are larger or smaller with growing magnitude. Of course, our magnitude range is very limited, but we'll see what we get in the future. Of course, due to the scale, the trend lines may show you a certain slope, but it is very small and with very bad correlation. Finally, values are extremely low for RQ value. As you heard in several presentations during the day, ground motion in case of strong earthquakes in Bucharest is dangerous for flexible structures with longer periods. And since we noticed this mobility with magnitude of a spectral shape, of course, one of the objectives here is to monitor at our seismic stations and to check if the phenomenon is confirmed in other points than each check. The range of magnitudes we have is much smaller, but even like this, you can start to see a certain tendency. And we hope the station will function more, and we will be able to confirm this as much as possible. Then we also try to better evaluate the site response. Of course, there is a debate in literature on the use of such borehole data because, as you have seen, especially in the presentation of Professor Gazetas, seismic waves are going up and going down and so on. So the records in the borehole are somehow polluted, we may say. But we said, let's check. And we made spectral ratios from the surface to the shallow borehole on the left and to the deep borehole on the right. And we compared the peak frequencies, the frequencies corresponding to peaks in the ratios, with what you get from a very basic and simple model of elastic behavior of soil with an average shear wave velocity, and you can see values are reasonably close for the main frequency. Well, my F1 is actually the F0 if you want to talk about the frequency of this package of soil. It's not for the whole soil at the site. It's just in between 0 and 28. You have some material, this material is vibrating, and the spectral ratio is capturing this. And we may look even to the higher frequencies, and the theory is working very well. The second mode or third mode, they are following the numbers and the relations from the literature for theoretical modeling of one layer with an average velocity. And of course, we were curious also about the global site response, and one way to look at it is the H over V spectral ratio using the seismic records. We present here two results from earthquake magnitude 6 and earthquake at magnitude 5. And you can see there is a peak at lower frequencies that came out. It is, and what is interesting for us is that this peak exists also deep in the borehole at 78 meters depth. And our interpretation was that this peak is related to the deep geology, otherwise it wouldn't be there. And we compared with some results from ambient vibration, which is the original way to use H/V ratios. So we identified a similar peak, but with ambient vibrations we identified even a lower frequency peak, bringing us to longer periods. The second drawing is in periods. So understanding the behavior of soil is still an ongoing research, as you have seen. And as I told you, we are just with some intermediate results, but still we could get few concluding remarks that the top 28 meters of soil are the main contributors for the PGA amplification. We found no correlation with earthquake magnitude in the amplification on the depth of the borehole. The spectral ratios surface over borehole captured, however, the vibration characteristics of the soil layer between the recording points. Soil behavior remained elastic, so even the magnitude 6 earthquake didn't bring any nonlinear behavior. And H/V spectral ratio indicates the effect of the deep geology. And since we mentioned so many times about Japan and the equipment they donated to Romania and the seismic station you have seen and everything, my acknowledgements go to Japan, to the Japan International Cooperation Agency. And as we learned from our Japanese colleagues, our thanks also go to the Japanese taxpayers, because they accept that part of their taxes are going to international development, to ODA, Overseas Development Agency, and we are grateful for this help they gave us. Thank you.
UTCB, viitorul e al tău, noi punem temelia. UTCB, construim pentru România. UTCB, Universitatea de Construcții Bucharest.